welcome to Introduction to Nanoscience and Nanotechnology course, lecture number 7. I'm Dr. Pervez Ahmed. In these lectures, we will have a discussion on physical properties of nanomaterials. This is the part number first of this lecture series, and here we will trying to explain the effect of size, shape, and compositions on the physical properties of nanomaterials. So let's proceed towards today's lecture. That is the effect of size, shape, and composition on physical properties of nanomaterial. So, physical properties, depend upon what depend upon the size, shape, that is whether the material, the nanomaterial is spare, rod, or plate, etc. And it's also depend upon the compositions. I mean, from what composition the materials that are being made. So the nanomaterial properties, it basically depend upon these three things. I mean that significantly enter the properties of the nanomaterial. So size, shape, and compositions, it significantly affect the properties of the nanomaterials. And along with that, also the crystal structure. I mean, it's important to know that whether the crystal structure is 4 center cubic or body center cubic, etc. So it also affect the physical properties of the nanomaterial. So we will try to explain each of them and details in the coming slide or in the coming lectures. So along with that, also the surface ligands or capping agents, it also affect the properties of the nanomaterials, uh, plus the medium in which they are dispersed. It also affect the property, particularly the physical property of the nanomaterial. So these are the phenomena which basically, the physical property depend on by the deduction of size from bulk to nano. That is size, shape, composition, crystal structure, surface ligands or capping agents, and the medium in which they are dispersed. All these are basically the factor which alter or which change the physical property at the nanoscale. So we will try to explain each factors one by one. So at first we will try to start it from the size. You know that randomly we have distributed, I mean, the size of molecules, nanoparticles, and bulk materials. And here you can view the size. Here we remember we have a rough scales, or we have an approximate scales for different type of the material. I mean, here you can see the molecules. So in molecules we can have a number of atom in between 1 to 10 atoms. I mean, these are the number of the atom that we can have in the molecule. And then we have nanoparticles. So nanoparticle can have the atom, approximate number of the atom in this particular range. I mean, we have from this range up to this range, we can have any number of the atom and the nanoparticle. And along with that, if you have more atom, that is more than 10 raised to power 6. So from here onwards, we have the bulk material. So we up to this particular scales we have the nanomaterial. I mean, nanomaterials mostly at the we have at the molecular level. So molecule, nanoparticle, and bulk material can distinguish by the number of atom comprising each type of the material. I mean, with the change in the number of atoms, the behavior of the nanoscale object, it also, changes to a great extent. So nanoparticles, which is a kind of the nanomaterials, exhibit unique properties due to their higher surface to volume ratio. And for that, in order to understand that, we are saying that at a nanoscale we have higher surface to volume ratio. Every time we are saying that at a nanoscale we have larger amount of the atom that are being found at the surface as compared to the volume. So here we will have some calculation, for example, or for a greater understanding of for the audience or the students. So for that we consider a spherical particle which has a diameter equal to 100 nanometer. Now from that we will try or we will exhibit that how the surface area is greater at the nanoscale as compared to the volume. So now utilizing this dimension or these or this diameter of the particular spherical particle, which is 100 nanometer, we will try to utilize we will try to calculate the volume and surface area of the nanomaterial, and we will try to explain that why we have larger surface area as compared to the volume at the nanoscale. So we start our calculation. So here we have for a sphere we have the surface area that is equal to 4 pi r square. Okay, so what actually we do here on, we put the values. You know that what is mean r is the radius. So radius and the relation, you know, the radius, the relation between the radius and the diameter. So here we put the diameter. I mean, once you put the values, you know that you multiply I mean, you know, the relation between the radius and diameter. So we just put the values, and here you got the relation that is pi d square. So here you just put the values. You put the values for the diameter, which is this much. So you do the calculations and you find the surface area equal to 3.141 into 10 raised to power minus 14 meter square. This is the surface area for spherical particles with the diameter equal to 100 nanometer. If you do the same for the volume, I mean, you do the calculation for the volume of that particular sphere with this diameter. So you know that we have the volume of the sphere, which is equal to 4 by 3 pi r cube, which is equal to pi d cube divided by 6. You just put the values and you do the simplification. You get the value for the volume, which is equal to 5.24 and 2 10 raised to power minus 22 meter cube. So here on you can see that which number is larger and how much is that larger. So if you do the comparison between the surface area and volume ratio, so this comparison gave us an approximate surface area to volume ratio of greater than 10 raised to power 7 to 1. I mean, this is the comparison. I mean, we have the calculation on the previous slide. On the basis of that calculations, if you do the comparison between the surface area and volume ratio, so you will find that this ratio is greater than 10 raised to power 7 to 1. I mean, if we have 10 raised to power 7 atom at the surface, so in comparison to that, we will have 1 atom at the volume, which is significantly larger than a micro sized particle. I mean, this is why we say that at the nanoscale we have enormous amount of the atom at the surface as compared to the volume. So as the surface area to volume ratio increases, so does the percentage of the atom at the surface and the surface forces become more dominant. I mean, with the reduction of size, we say that the surface area increases, and also when the surface area increases, so along with that, the forces that are operational at the surface, they also become dominant. So the particle, as a result, we have I mean, it's a generally accepted properties of the materials that is being derived from the bulk, that we have the percentage of the atom at the surface at the nanoscale. So these properties changes at the nanoscale. So what it mean? It mean that the properties I mean, when we have larger amount of the atom at the surface, so larger amount of the atom, they come in contact with the other material as compared to the bulk material. So in bulk we have majority of the atom at the volume. So majority of the atom, they are unable to expose to the external environment or to ambient environment. So at nanoscale we have majority of the atom at the surface, so they have the capability to react more actively, more prominently as compared to the bulk material. And now this phenomena I mean, is generally accepted properties, I mean, that is being derived from the behaviors of the nanomaterial, and everybody know about this kind of effects now. So size, some example calculation for the volume and surface area of nanoparticles. These calculations use nanomaterial as unit of the length, and here you can see for yourself that how when we change the diameter of the nanomaterial, that is nanoparticle, so along with that you can see that how the volume and surface area increases, and when this changes, so along with that you can see that how the surface area to volume ratio changes. I mean, here you can see that I mean, here we have the particles, the particles diameter started from 1, and then we have 10, 100, 1000, 10,000, 100,000, and 10 100,000. So here you can see that when the diameters of the nanoparticle changes, so along with that, we also have a change and the volumes of the nanoparticle. I mean, with the increase in the diameter, the volume of the material, it also increases. So here you can see it for yourself that once the particle size increases, so you can find a decrease uh, surface area. I mean, here you can see that we have surface area. The surface area is also I mean, increases. Here you can see it. We have surface area in nanometer, that is 3.14. Then you can see that we have this number for surface area to I mean, for surface area it's also increases and nanometer. But if you compare this, I mean, with the surface area to volume ratio, so here you can see by yourself that when the number of I mean, the nanoparticle diameter increases, so here you can see that the surface to volume ratio, it decreases drastically. I mean, here you can see that for a smaller scale, for smaller diameter, we have I mean, a very big number, that is 6 surface for surface to volume ratio. And then for 10 atoms or for 10 nanometers, you can see that the surface area to volume ratio, it increases to 0.6. And then for 100 nanometers, here you can see that the ratio is decreased to 0.06. And if we further increases the particle size, that is up to 1000 nanometer, so here you can see that the ratio is being reduced to 0.006 nanometers, nanometer for a nanometer cube, nanometer square to nanometer cube. So this is a very simple example from where you can learn that how the increase in the particle size affect the surface area to volume ratio. I mean, it's a very easy example, and very easily you can do the calculation. You can also solve the problem, particularly when you are trying to do the research, you try to perform the experiment, you synthesize nanoparticle or nanomaterial. So from that onward you can calculate the surface area to volume ratio, and with that you can also further affect the other properties, that is the catalytic activity, or means some other reactivity or some chemical properties with the help of these calculation. So if you look at the graph, so in this graph here you can see that we have surface area and nanometers square, and we have the volume and nanometer cube. So here we have plotted I mean, surface area to volume ratio versus the nanometer, the nanoparticle diameter. So here you can see that the ratio increases significantly or drastically when the nanoparticle diameter drops below 100 nanometer. I mean, here you can see it for yourself that once the diameter start dropping from below 100 nanometers, I mean, here you see that we come towards below 100 nanometer. So you can observe a drastic change in the surface area to volume ratio. I mean, surface area to volume ratio increases significantly once the material size reduces from 100 below 100 nanometers. So at the as the percentage of the atom at the surface increases, so the mechanical, optical, electrical, chemical, and magnetic properties, it also changes. I mean, um, once we are at the nanoscale, I mean, we are below 100 nanometers, so all these properties, they are dramatically changes from their bulk counterpart. And a good example of that, I mean, as I mentioned in the previous lecture, we will discuss it in the coming lecture when we will try to explain the optical properties of the material. So here we just gave a sort of example of the optical properties of the gold and silver. So you will find that uh, the optical properties of gold and silver changes to a great extent when the spatial dimension are reduced and concentration is being changed. I mean, you will find that If you have gold nanoparticle or you have silver nanoparticle, so if you reduce the dimensions or you reduce the concentrations of these particles in a solution, so you will find that how their optical properties, we mean the color of these material will change. I mean, you will change a significant change and the color of these material with the reductions of size and concentrations of these materials. And here is a good example of that. I mean, it's visible. I think it's clearly visible here. I mean, here you see we have nanoprism. I mean, it's a silver nanoparticle, approximately 100 nanometer. So here you can see how it look. I mean, it's almost look like dark red at 100 nanometers. But if you reduce the size, I mean, here you can see that up to 100 nanometers, from 100 nanometers up to 80 nanometer. So you can see, I mean, how the color has been changed. Or if you change this to 40 nanometer, so you see here what's the color look like. And if you increase the diameter above 100 nanometers, so here you can see it how it look like. I mean, above, I mean, a significant change is observed at 100 nanometers and above 100 nanometers. That is around 100 nanometers. I mean, it's the colors, you can see it for yourself that how it look like. And this is the electron image. I mean, SEM image of the material, SEM image of the material. I mean, how it look like. And here you can see that at 120 nanometer, how it look like. And similarly, once you I mean, you have gold nanoparticle, gold spares of gold nanoparticles, or sorry, you have spares of gold. So at 100 nanometers, I mean, the look is like this. But if you reduce this to 50 nanometers, the gold spare, so here you can observe the change of the materials, the change in the look or the change in the color of the material. So that's how the optical properties or the color of the material changes at the nanoscale. And along with that, if you reduce the size of the material, so the size on not only affect the optical properties or the color of the material, but it also increases, it also changes the physical properties, which include the melting point of the materials. I mean, it also changes. So melting point is a function of the particles as been plotted here. So here you can see that that is the melting point of the nanoparticle have a lower I mean, the nanoparticle have a lower melting point than their bulk counterpart. And here you can see it. I mean, it's the diameter of the materials, and this is the melting point in Kelvin. This is the diameter in angstrom. So here you can see that I mean, when the size is reduced, I mean, it's with the reduction in size. So here you can see that how the melting point is being reduced. So with the reduction in size of the materials, it's not only affect the optical properties of the material, but it also significantly affect the melting point of the material as well. So melting point, if we plot, if we observe melting point versus shape, so melting point also changes by the shapes of the material. For example, if we have particle, so particle may center together at lower than the expected temperature. I mean, if you have nanoparticles, so nanoparticle may center together at lower temperature than the expected temperature. And if you have rod, so rod can melt and form spherical droplet if heated too high. And if you have film, from film we mean thin film. So thin film can form pinhole. I mean, at a smaller scale, they can form pinhole. That can and if you try to continue heating up that particular material, so it can lead to deviating behavior and island formations. I mean, deviating, that we will explain later on that what it mean by deviating. And along with that, it will form island if you further heated the thin film material at the nanoscale. So that's all we have for this lecture. Hope you enjoy and learn a lot. Thanks for watching. See you in next lecture with more interesting facts that affect the the physical property of the nanomaterial. So stay tuned for the next lecture, that will be lecture number 8. And in that lecture, we will try to explain the crystal structure that significantly affect the physical property of the nanomaterial. So stay tuned with us. Till then, bye bye.